Now, the person Wöhler is a German guy. He wanted to investigate what stress level should be subjected to the axle, so that we will not have failure or infinite life. So he started studying that during the experiment, doing the rotating bending machines, and he came out with the concept of stress life or SN approach or curve. So later on in the second quarter of 20th century, a committee was organized for fatigue research. This is called ASTM Committee E9, which is American Standard for Testing Material, E9 for the fatigue studies. They have different subcommittee. So during his study, he did rotating bending with constant RPM. He has put 2 specimens, so that in one go 2 specimens will be tested, and it is simulated as a axle railway. See, 90-degree it will be going through. Once you have a cantilever tip loading, and once it rotates, obviously it will be seeing one end positive, other is negative. It is a bending, and that is achieved by providing the bearing. So to generate SN curve, what he did is the usual way is you take a specimen subject to certain stress ratio and cycle it, and note down how many number of cycles it takes to failure, and join those points to get a SN curve. So this example says R is equal to 0. In 1 point sigma max you are taking red color. It's showing 3 dots because your fatigue phenomenon is depend on the surface condition, and unlike in static result, you are not expected to have a variation of 1%. In fatigue is easily 20 to 30% is allowed. So you will have a lot of scale, then you join the points from beginning to end to get a SN curve. And please recall previous slide, it was a non-linear, right? This is, and your y-axis is sigma max. It can be stress amplitude. Also, I will keep insisting you, whenever you are referring to SN curve, please see whether it is a stress amplitude or S max or S max net stress, because if you refer to MMPDS, they will be giving mostly S max net, and it's a non-linear, that is linear log scale. But once you plot log scale, that's a log scale, you will get a straight line, and you have a lot of variations. You have a bottom line, top line. The one which is reported your MMPDS, ESTU, handbook or textbook, that always give the mean value. And so no single results of fatigue life obtained correspond to given S max level will be constant. It always varies with log normal range, and to take it account, you do include the scatter factor to take care of the such variation. And this is the typically scatter one can see while generating a SN curve from the testing. See here we are showing y-axis range. It can be that means it's not wrong. It can be stress amplitude, it can be stress range, it can be sigma S max also. So you see at lower you have a lot of scatter, and this arrow mark is not failure. And this is what the journal there. So SN curve is what reported is a center midpoint of all the points set together. I'll tell you why the significance of insisting that y center line, because if you have heard of scatter factor of 5, that 5 is derived based on that. This is a 50%. Now this is a typical SN curve shown both ferrous and non-ferrous. You can see the clear distinct knee point here, which is 10 to the power 6, which is called the endurance limit. And unfortunately in the aluminum, which is there is no well-defined knee point, it asymptotically keeps on decreasing. So it brings to 2 definitions. One is called endurance limit, below which you will have a 10 to the power 6 per. It is well defined. 10 to the power 6 is the benchmark for the ferrous material. But in aluminum alloy, there's nobody says what is the endurance limit for aluminum. Nobody talks about that. They say what is the fatigue strength, and that is the definition. And but somewhere you have to stop in the calculation, right? So the benchmark is 5 into 10 to the power 8 to consider equivalent to the endurance limit. And this is the example. You can see the well defined. So any structure designed from the ferrous material, if you design a structure to ensure the operating stress below coming to the endurance limit of the material, you will have infinite life. That is what ground vehicles are able to run with overloaded. whether the bus vehicle, you see the not only overcrowded, people will be sitting in the top with thing, nothing happens because weight is not criteria in the ground vehicle, and they are designed in such a way the stresses come below the Anderson, it will have infinite life. But in the case of aluminum alloy, unfortunately there is no such knee point where you can design. Even if you design below that, still it damage keep on accumulating. Okay,